Okay, so we know everything there is to know about hyperplanes and geometrical manipulations. In 1960, people have started thinking about, can we use those hyperplanes, not just setting them up, but learning them from data. Remember our empirical risk minimization, all we have is data samples. Can we actually come up with an algorithm that learns the value of W from looking at those data samples? And Frank Rosenblatt, this gentleman on the figure, actually suggested that algorithm, and inspired by the way how neuron works, called it perceptron, as a modification of the word neuron, perceptron, something that perceives. And here he is on the picture in front of a hardware implementation of that perceptron on Mark I machine. Rejoice those who have Python and import torch or TensorFlow command. So back to the hyperplane. If we draw our hyperplane equation, lots of things are in science are about seeing things at the right angle. So W transpose X equals 0. That's equivalent to this picture, right? We have values of X that are multiplied by the weights components of the W. They're summed up, and then they have a threshold. If they're on one side of the threshold, the output is positive, and if they're on the other side of the threshold, the output is negative, or it's 0 if they are on the hyperplane. So after drawing this figure of this linear discriminant, Frank Rosenblatt, I assume, got inspired or saw connection with the neuron discovery. And neuron was discovered by Ramon y Cajal, and this is one of his hand drawing of what he saw in the microscope. He basically discovered a specific form of staining that would reveal those neurons in rat brain, I believe, but basically in mammalian brains. And the way this neuron, the actual neuron in our cortex and mammals' cortex and in other organisms is working, is very similar, or was kind of inspiring to why the linear discriminant was called perceptron. The neuron has dendrites, which are connected to axons or outputs of other neurons, and it has cell body, soma, and an output, axon. Once the action potential, once the potential of the soma increases some threshold, which is called action potential, the neuron produces an output, it fires. So what perceptron does, it has input through dendrites, so they're weighted, so they have different strengths, each dendrite, and the quote-unquote dendrite, of course, affects the input differently. So if this input is not as important, the weight is small. If this input is negatively important, the weight is negative. And if this input is super important, the weight is high, and so on. So you see the analogy. It's still the same geometry. We're still in a simple vector space. But once people started thinking about this linear discriminant biologically, and it opened up a lot of ways of how to consider new methods, or how how to work with those linear discriminants, maybe with a rotating hyperplane, which we are still. But it's much more fun to think about neurons, and we humans need inspirations, and we humans need inspirations. And this rebranding of a linear classifier into a perceptron attracted a lot of attention to the field of artificial intelligence. It's kind of created machine learning and created the learning field in general. So all of those products of the inputs with the weights are summed together and then thresholded with non-differentiable threshold function. That's important. And then returned as an output, and if the output is incorrect, then there's perceptron learning rule that we will just go into shortly. So very similar or analogy to a neuron, by analogy to a neuron, very simplified version. Okay, so how do we optimize all of that? How do we learn, especially given that this is a non-differentiable function, and as I told on the one of the previous lectures, we are not going to use gradient descent. Well, first of all, we need some criterion or objective that we will optimize. And our criterion is this. Notice it's the distance of the point. Well, assume the W is unnormal. Let's call it unnormalized distance of a point to the hyperplane, and multiplied by the label. And we only consider incorrectly classified samples. So incorrectly classified samples, let's change our color, will be those for which this value is less than 0, right? We already considered that for correctly classified samples, this should be positive. This value should be positive. So for all incorrectly classified samples, this will be negative, and this criterion with this minus sign in front will be positive. So we want to minimize that number, and well, ideally there is nothing incorrectly classified. And W is parameters of our model, so those weights of the perceptron. There are two algorithms of the perceptron. One algorithm is batch. It considers the whole data set at once. And in batch perceptron, we have batch perceptron algorithm. We have a few inputs. It's our initial value of the separating hyperplane normal, some learning rate. A learning rate can depend on iteration, so learning rate function. Some criterion is when to stop, and we initialize our counter of iterations. In the end of the batch perceptron, we return our W, our solution hyperplane. So what this algorithm tells us is repeat until this criterion is less than some threshold. So if there are no points in the so Y is the set of samples misclassified by this current W, current hyperplane. If there is nothing misclassified, this is 0, and we're definitely less than the threshold. But what we do, we go through multiple iterations, and at each iteration we update our W, the current W, with some learning rate discount of the sum with the sum of L, the label, times X. only for misclassified samples, but for all misclassified samples at once. Another algorithm that is called stochastic algorithm, or stochastic perceptron. For stochastic perceptron, all we do is we initialize the W and set the counter to 0. And then we keep going through our data set one by one, linearly, just touching each point and checking if it's misclassified by W. That is, notice, if LK times W transpose XK is less than 0, then we adjust the W by LK XK product. So label times the value, the actual location or the actual data sample. So, and we do that until all patterns properly classified. So that's kind of interesting, right? Why would that even work? So we take the W, remember the two-dimensional? Sure. We have W here. We have samples of one class on this side, and we have samples of another class on this side, and the W yeah, the W goes, I think this is the current W. Well, we don't have a misclassified in this picture, but if there was one or some misclassified that, say, here, so this sample would be misclassified because it's negative. Let me change the color so you can see what I'm talking about. So if this sample is misclassified, we're just saying, oh, okay, add this sample times the label, which is here. We already multiplied the label, right? And ta-da, jump over there. And keep doing that jerking motion back and forth until you converge. Will you converge? Well, surprisingly, and we will prove it now. Stochastic algorithm convergence theorem. If the training samples are linearly separable, this is very important modifier or requirement. If they are linearly separable, then the sequence of weight vectors in line 4 of algorithm 2 will terminate at a solution vector. Surprisingly, again, look what is happening. So, we have some random hyperplane. We multiplied our points by their sign. So those are points of one class, those are points of another class. And as long as they're all on the positive side, right here, everything is fine. But then, if there is one point on the negative side, that's Li W transpose Xi is less than 0. We just make a step and totally, quickly, not smoothly, change the location of the hyperplane. And then do it again, because now all of those three are misclassified. So say we check this one, and we check and jump here. And through this jumping motion, like we constantly get jumping motion, we again misclassify these labels. Why should it work? Why it converges? So what Rosenblatt has done, he proved that this algorithm converges, and let us try to prove it too. So let us show that for any solution W tilde, the following holds. So W tilde is the dataset is separable, and W tilde is a separating hyperplane that does separate the solution. And okay, so we need to show that K is our iteration. We want to show that for the next iteration, what we have is closer, the distance from W at the current, at the previous iteration is larger from the optimal. Or it's not, look, it's not optimal, there is no optimal in perceptron per se, anything that separates two classes. Again, we need another picture. So there are multiple hyperplanes that would be a solution. So W tilde is any of them. It's something that separates the classes. So we just need to show that with this algorithm, with each iteration, we'll get closer to a solution, W tilde, or be no worse, less than or equal to. Let's try that. So this is our line 4 in the algorithm, right? Our next wk plus 1 equals wk plus misclassified xk times its label. So we know that for true for the solution, this holds. For W tilde is a separating hyperplane, so this inequality holds. Then if we rewrite this equation by adding to both sides minus alpha W tilde, nothing changed, right? We added the same thing to both sides of the equation. It's just the same equation. And then if we square both sides, nothing will change either, right? It's just the length of the this vector versus the length of that vector. Because if this equality holds, that means the vector, see, this is a one vector minus a scaled version of another vector equals yet another vector. The equality signs, that means they're element-wise equal, which that's how we got wk plus 1. But if they're element-wise equal, the length are equal. That's what we've done here with adding L2. So now the left-hand side stays the same, but let's open up the right-hand side. What? Let's try that. So what we have, just going slow. There's nothing scary here, but I want you to understand how these things are done. So scalar, a vector. Sorry, this is an x. So what that square of L2 norm tells us is just that, W k minus lambda W tilde plus L k x k. And When we multiply those two, we do the transpose, but this times that transpose is nothing but just the L2 norm squared. Let me actually spell it out. So what happens, because we're multiplying two vectors, there is a transpose here. So we started at the vector norm of one vector, but we know its equivalent of vector norm is a number. Just so you know, but then we squared. So this x is what's inside, and I'm working through so you are comfortable. Right, this again is nothing but L2 norm squared, so we write it here. The next part comes in two pieces. One is we take this and multiply it by this. We get WK minus lambda W tilde transpose LK XK. But then we get another one. We get LK XK transpose times WK minus lambda W tilde. But notice here that this is a scalar and this is a scalar, and it doesn't matter if you get a scalar this way or that way. So they're equivalent. That's why we just sum them up and have a 2 here. The answer is the same. And then you get the norm here. So that part is clear, I hope. Or pause and derive. Well, I'm not deriving here, but you can just derive this part. Transpose, blah, blah, blah. You can do it. So now we just follow the algebra. We bring this inside or multiply through. Nothing else happens here. Simple manipulation for now. And then we know that the step 4, remember, in the stochastic perceptron algorithm, the step 4 happens only if xk was misclassified. So because xk was misclassified, we know that this holds. So it's less than or equal to 0. This expression is less than or equal to 0. So it is negative. Because it is less than or equal to 0. The W, okay, it's negative, and we're simply dropping it. Oops, my mouse, let me think. Okay, I found a problem. I missed a 2 here. That's why. So there is no 2 here, but now I added it back, and then it makes sense. So this is negative, and if we drop it from equation, then the remaining part is larger than it was before because we're not subtracting that part, right? So okay, just since xk was misclassified, this part is negative. We're removing that from equation, and what we obtain without this part is larger than what we had before. that's why instead of equality, we now have, well, and again, maybe it's 0, right? It's less than or equal to. That's why we replace it with the less than or equal to sign. And I will cheat a little bit. I will fix my slides on the fly in the lecture. That's my cheating. Okay, up to this part is clear. Okay, alpha is just a positive constant, right? So some constant. We don't know yet. So we established this so far, that W at the next iteration minus scale version of our solution W W at the next iteration minus scale version of our solution W, the distance or the length of that vector is less than or equal than this number, and it's a scalar number. You can be sure of that. Let's introduce beta squared. Let's just call beta squared is the maximal norm, squared norm of our data samples, and misclassified in this case, but yeah, maximal norm because we are only considering misclassified samples, but I guess any pattern vector, because that would be simpler to think about it, since the label is just a sign, plus or minus. It doesn't matter because we're squaring. That's why we drop the label. So we have maximum norm. Beta square is the maximum norm of a sample. Gamma is, let's introduce gamma as well, the smallest inner product of the solution vector with any pattern vector. So we have beta squared, maximum length of pattern vector, squared, and we have gamma. We're just, again, just definitions. Let's just introduce so we can simplify what we see on the screen. And what gamma tells us is let me try to give you an notation. So we have a hyperplane that has, well, I intended for it to go through the origin, but okay, just pretend. So we have a hyperplane that is a solution of two classes. What this is doing, well, we removed the sign, so it, like, I'm drawing it slightly differently. But what we mean here is we're taking a sample for which this distance to the hyperplane is minimal. So we're taking a sample that is closest to the hyperplane. So not this, not that, but maybe this, maybe that, or maybe there is one right here, or one right at the hyperplane somewhere. So that's our gamma. That is our minimal distance to the hyperplane. So if you look at here, so we took the smallest value here, gamma, and we took the largest value here, beta. So we're saying we will add maximal what we can add, and we will subtract minimal what we can subtract. So our bound holds. Well, our bound holds regardless for any values, but we are saying this is the furthest bound, like we are furthest apart. The right hand side is as large as it could be for this specific data set. That's what it says here. Okay, and if we set our alpha to beta squared divided by gamma, then we will end up with the following inequality. Just plug alpha here and you see that you get minus 2 beta squared plus beta squared, and you are at minus beta squared. The distance to the solution at each step is reduced by at least beta squared. So at each iteration, that's what this says. So at each iteration, it's at least the inequality less than or equal to. So we had that distance, and we subtract. Well, it's possibly reduced more, but because we took the largest, remember by this gamma and beta assumptions, this is the largest possible value. But if it is smaller, then that means the reduction, or actually this is the largest possible value, means this is the maximal possible reduction, I guess. Okay. So, final steps. We arrived at this inequality, and after k iterations, so we know that we are reducing by at least beta square, and after k iterations we are reducing by k beta squares. If we start with 1 and we get to k plus 1, we made k minus k beta squared reductions. So, and the distance, this part, cannot become negative, so it cannot be less than or equal to some negative number. So this number can only be positive. So we can rewrite what k maximal number of iterations is. So we cannot do more than k0 iterations, and yes, k0 is just this ratio. If you plug k0 in, you'll get 0, right? So we bounded, we know how many iterations this algorithm will make in order for our W to get to a solution W within a 0 distance. So if we initialize W1 with 0, let's start with a 0 vector, and then we can, so that's what we're getting, alpha squared, so just algebraic manipulations, and we defined alpha as beta squared divided by gamma. Remember? And when we plug that in, definition of alpha. Wait a second, let's check. Was it beta squared? I think it was beta squared divided by gamma. Yes. Yes, okay, everything works out. So alpha squared is beta 4 alpha squared, gamma squared, and that's how we get gamma squared here, beta squared and beta to the 4th are cancelled, and then we'll just plug definition of beta squared. It's the maximum value of the pattern divided by the point that's at the minimal distance to this final solution. Remember, there are many solutions, and if your final solution by chance will end up in such a way that there is a point super close to it, this value is super small. This is a small value, and this is any reasonable value. For any reasonable value, this can go as small as it could, and your k will be the largest. It's kind of counterintuitive. If your algorithm converges, but if it happened to converge such that one of the points is very close to the solution, the number of iterations will be maximal. Think about it. And that should help this whole proof and this inequality. You will work on it in your homework. It's all covered and explained in the homework. Explained. You will explain it to yourself by going through the homework, but that will become super easy.